Good day and welcome back for the second part of our discussion on strategies for integration. In our previous video, which I know was a bit on the longer side, so I apologize for that, we discussed strategies for integration. That is, if we encounter an antiderivative and we are unsure how to evaluate, what are some questions we can ask ourselves or some steps we can go through to hopefully determine the method of integration. Now, if you look at an example and you immediately know how to evaluate it, that's the ideal scenario. You just go ahead and evaluate. And then if you're unsure how to evaluate it, you now have kind of a thought process that we've built up. And remember, when it comes time for the exam, one of the difficulties is we are not going to tell you what method of integration to use, but instead, based upon your experience and intuition, you are going to have to decide on that desired method of integration. So what I would like you to do at this point is to pause your video and think about how you would approach this integral. And there's multiple things we can try. Usually I find when discussing with students, the first suggestion I get is, hey, it's a polynomial times an exponential, let's try an integration by parts. That is a very reasonable approach. So we'd say, okay, our experience with this is to let u be x to the fifth and dv be e to the minus x cubed. And do you see the issue that we encounter? To apply integration by parts, we need to anti-differentiate e to the minus x cubed. But I have no idea what that antiderivative is. So we need a different approach. The next possibility that might jump out to us is, how about trying a substitution? We do see this inside function, x cubed, and I don't know, its derivative is somewhere in that outside function. So we could try, let's call it w, to be x cubed. If w is x cubed, dw would be 3x squared dx. And we can get an x squared out of our integrand. We can write x to the fifth as x cubed times x squared. And note, lo and behold, this x cubed that's left over is w. And x squared dx is 1/3 dw. So it looked a bit more difficult to get started, but we have a 1/3 that pulls out, and we're integrating w e to the minus w. And this is a good feeling part of the problem because this is a standard form that we know integration by parts will work well. So using integration by parts, we would want to let u be w and dv e to the minus w. So du is dw, v is minus e to the minus w. Integration by parts is uv minus the integral of v du. So we have the 1/3 we'll be careful of out front, minus w e to the minus w, and we're subtracting away the integral of v du. But note in v we have this extra minus, which will turn the minus out front of the integral into a plus, and we're integrating e to the minus w. So distributing through the 1/3, the antiderivative of e to the minus w is minus e to the minus w, and we have our plus c. And note, we're not quite finished because we need to resubstitute. So we will make each and every w an x cubed. So finally we have minus 1/3 x cubed e to the minus x cubed minus 1/3 e to the minus x cubed plus c. So let's look at another example. Our next example is a definite integral from 0 to 1 of 1 plus the square root of x raised to the 8th power. Now I want to note I've chosen 8 in this case to be large enough to keep this interesting. If this was simply 1 plus the square root of x quantity squared, then you would just FOIL it out and anti-differentiate term by term, which would be perfectly fine. With it being raised to the 8th power, I would be really impressed if you went through the trouble of expanding and multiplying everything out to anti-differentiate this. And even though that's maybe not the advised method, that's certainly a choice that you could make, and it's certainly a method that could be applied. Instead, what I want to note is there's a different approach we can take. So if you go through our list of things, there's no kind of obvious manipulation, at least that I want to do here algebraically. There's no obvious substitution. It doesn't fit any of our standard forms. I don't see a good way to apply integration by parts. But is there a more subtle substitution we can make? And at this point, I want you to pause your video and think, if you had to make a substitution, what could you let u be equal to? When it comes to making a substitution, an ideal choice for u can oftentimes be, an inside function, and furthermore, the largest reasonable inside function. And with that in mind, we can try u being 1 plus the square root of x. Well, if u is equal to 1 plus the square root of x, let's manipulate this a little bit. So algebraically, we could say square root of x is u minus 1, which forces x to be u minus 1 quantity squared. And dx is 2u minus 1 du. So not worrying about our limits of integration for the moment, 1 plus square root of x is u, and it's raised to the 8th power. Dx becomes 2u minus 1 du. And I am going to add my limits of integration in here, but first I want to note that this is very reasonable. The constant 2 pulls out, and the u to the 8th can distribute through and hit both the u and the minus 1 to simplify as u to the 9th minus u to the 8th. So a very reasonable antiderivative. But as usual, whenever we have a substitution with a definite integral, we must change our limits of integration. So using this substitution, in terms of x, the lower limit of integration is 0, which implies the lower limit with u is 1 plus the square root of 0, or 1. The upper limit in x is 1, which implies for u it would be 1 plus the square root of 1, or 2. And now we can finish up by evaluating this equivalent definite integral. So term by term, the 2 is going to hang around, but we have 1/10 u to the 10th minus 1/9 u to the 9th from 1 to 2. So replace each and every u with a 2, minus sign, substitute in 1, which gives us the following. And note you could do some algebraic simplifications, but remember when the question simply asks you to anti-differentiate or evaluate a definite integral, once you get it down to that answer, I would leave it in that form. And just for fun, I'm going to go ahead and add in an extra example. So I guess if you stuck around this long, fantastic, hopefully everyone has, you get, I think, what they would call bonus content here. So let's go ahead and investigate the example of the antiderivative of sine of 2x times the natural log of sine of x. And at this point, I would like you to maybe pause your video, give yourself just a minute, and see if you can come up with an approach. How do you think you should approach evaluating this integral? And this one really is a bit subtle to get started with. But one bit of intuition is, even though this doesn't look familiar to anything we've previously encountered, you have this sign inside the natural log. So it would be perfectly reasonable to do a substitution, or at least attempt to do a substitution, right? There's never any guarantee until we try. So if w is sine, dw is cosine x dx. And can you think of any way to rewrite sine of 2x to get this cosine x to fall out of it? And hopefully you are recalling the double angle formula for sine. Sine 2x is 2 sine x cosine x. So pull the 2 out front, rewrite this as sine x cosine x, natural log of sine x. So in terms of w's, we have w, and then the cosine x dx is our dw. So immediately upon making this substitution, no, we haven't solved the integral by any means, but this looks much more reasonable. And the reason I would say this looks much more reasonable is w times the natural log of w can be integrated using integration by parts. This is one of those kind of standard forms where integration by parts will apply. So if we're going to use integration by parts, we need to make a choice. What is going to play our role of u? What is going to play the role of dv? And there is one good choice to make here. So pause your video and just take 30 seconds to determine what will be u. And note, unless you want to do a separate integration by parts, you will want to choose u to be the natural log of w. Because the natural log of w is a function that we can quickly and efficiently differentiate, not so much with the anti-differentiation. That would require integration by parts. So applying integration by parts, we'll let the 2 hang around out front, and we'll have uv, 1/2 w squared natural log of w, minus the integral of v du. So I'm going to pull the constant 1/2 out front, and w squared times 1 over w is a w. And to make sure there's no confusion, this w comes from w squared times 1 over w. And then we evaluate this remaining antiderivative and probably simultaneously distributing that 2 through. So we have w squared ln of w hanging around out front, and an antiderivative of w is 1/2 w squared. And finally, we resubstitute. Turn each of these 3 w's back into a sine. So sine squared, natural log of sine, minus 1/2 sine squared. And I definitely would consider this to be a more difficult example, but my hope with this is that when you see the method to use, all of a sudden it doesn't seem nearly as bad. The hardest part for some of these problems, especially the 2 examples on this page, are getting started. What is our initial approach going to be? So remember, there's plenty of good suggested problems in the textbook. There are 41 odd problems asking you to evaluate an integral. Those odd problems have answers in the back of the book. And as usual, do not hesitate to reach out when you have questions. Drop me an email or stop by the office hours. Stay tuned. Take care.